in PMMC, we saw there were permanent magnets which were providing a flux, right? A flux is required to maintain the magnetic field in any instrument. And why magnetic field is very important? Because magnetic field is something which provides magnetic force, and force is required to move the pointer, right? Or move the pointer in that instrument which we see when we connect any instrument like PMMC instrument. So for that, magnetic field is very important. So in PMMC, permanent magnets for generating the magnetic force. Today we will see another instrument, that is electrodynamometer. Okay. So in the name itself, it is mentioned electrodynamometer. So what will happen here? Any idea?
Magnetic property due to electric current, sir.
Yes, right, correct. So magnetic field can be generated by two ways, right? One by permanent magnet, other by electromagnet. So one coil will be placed, right? That will generate magnetic field, and rest of the circuit will be exactly same. Our This coil will be exactly same, whatever the way it was before. And field current, we will call it field current. In DC machine also we call it field current, right? So this field current will travel and it will produce flux, right? If current is traveling in this way, so if you curl your fingers, right? Oh no, it should be this way. Okay, this. So either this way, the force will act, or if you reverse the current, the force will be other way around. So in PMMC, we saw torque is equal to B A N I. Right. So here one thing will change. B will depend on IF. The more the field current, more you will get the magnetic field. So the moving coil will experience more force when IM or IF field current is higher. So force will be higher if IF is higher, right? And hence torque will also be higher because torque is dependent on force. So now in electrodynamometer, one thing is different from PMMC, that torque is directly proportional to IF into IM. IM is the current of moving coil, right? This is the moving coil. So IM is the current for that. Okay. So, but dependent on those two currents make this instrument non-linear, right? Because earlier this torque on PMMC, it was dependent simply on current, right? So torque was linear. So that is why PMMC device is linear, right? But here it is IFIM, and if you see, if IF is equal to IM, torque will be proportional to I square, equal to I, isn't it? So from the property, you see that behavior of this force in this instrument will be non-linear. Okay,
Yes, sir.
right. So now we are sure that torque is dependent on IF and IM. One more thing is involved here. Since in permanent magnet, flux was almost constant. Okay. But here, one more term will come in picture. In last lecture also I discussed, but I did not explain in detail. I wrote one expression, TD is equal to IF, IM, and dm by d theta, right? So what is dm by d theta here? Hmm? And why dm by d theta is coming in the picture? So for your information, I am telling M is the mutual inductance, right? So mutual inductance comes in picture, and mutual inductance is a parameter which defines that how much flux is being linked in both the coil, right? So if, let us suppose, if in example also, lecture example also, if there are two coils and they are placed far, and they are, and one third coil, coil, so coil 1, coil 2, coil 3. So the flux linkage will be maximum if current is flowing only in coil 1. Okay, then which two coils will have the maximum linkage?
One, two.
Because in coil 2, exactly, that's correct. So in coil 2 will have the maximum linkage. In that case, the M will have the maximum value. In that case, torque will. So that is why in layman words, when I was explaining that more the magnetic field, more torque will be there. So that magnetic field is justified by mutual inductance. So mutual inductance is the parameter which will amplify this relationship. So how much flux is being linked by two coils, right? So if two coils are closer, all current is higher, then your mutual inductance is higher. So the expression for mutual inductance is written as that voltage induced in second coil divided by change in current of first or source coil, right? So basically, this is very basic voltage equation. V is equal to M di by dt. Or you might have seen V is equal to L di by dt. So that is self inductance, that is mutual inductance, isn't it? So this is the basic expression of mutual inductance, right? And since coil, and why dm by d theta is very important here, because coil will be rotating. So let's suppose, so because of this, flux is, because of this current, this type of current, let's suppose a flux is traveling in this direction. Okay, and this moving coil is there moving. So the maximum linkage will appear when moving coil is in this position, right? And the minimum linkage will be in the circuit when the moving coil is exactly parallel to the direction of the magnetic field. So when the moving coil is 90 degree to the,
सर आवाज नहीं आ रहा। आवाज नहीं आ रही सर। आवाज नहीं आ रहा है सर।
Am I audible now?
यस सर।
Okay, great. Thanks. Thanks a lot. Okay, so let me repeat it if you have missed this. So I have provided some data to solve deflecting torque. So I have provided mutual inductance, which is varying with theta, as we saw just now, 500 sine theta minus pi by 9 microhenry. K is given, that is a spring constant, 0.15 micronewton meter per degree. And deflection when the deflection is 40 degree in equilibrium, we need to find the deflecting torque. So I hope I was audible during the explanation of electrodynamometer. If there is any question from the explanation of electrodynamometer or theory of electrodynamometer, you can ask if you want.
सर प्रीवियस स्लाइड से आवाज नहीं आ रहा था.
Oh, you have question from this slide? Okay.
यस सर, यस.
Please ask.
इसी जगह से आवाज नहीं आ रहा था.
अच्छा, यहाँ से आवाज नहीं आ रहा था क्या?
यस सर.
Okay. So let me explain it once more. So see, we were certain till deflecting torque is directly proportional to moving coil current and field current, right? And dm by d theta is coming in picture because when moving coil will be facing with this purple position, then the linkage will be maximum. You agree?
Yes,
And
sir.
at that time, torque will be maximum because torque is dependent on position along with the currents, both the currents. And when the moving coil is in the position of this blue position, then the linkage will be minimum, right? And torque will be zero. Ideally, torque should be zero at that position. Right? And at equilibrium, when there is no oscillations, the oscillations have been damped out by damping torque, then we can equate it to k theta, right? So this is the expression of deflecting torque. This is the equation of a spring torque, and we can equate it further. So theta or deflection we can get Im If by theta into dm by d theta, and Im If we can consider constant, right? Sorry, Im If by k here. Im If by k into dm by d theta. So this will be deflection of the pointer in this electrodynamometer. So based on this theory, we went ahead with this question. We are trying to solve this question to gain more understanding of the electrodynamometer. So is there any question from this slide?
No, sir.
Okay, great. So let us solve this problem, shall we? So we need to find out the deflecting torque. So what should be the approach to calculate deflecting torque? Please let me know. So we have seen TD is equal to Im If by K into dm by d theta. Sorry, no. Im If into dm by d theta, right? And at equilibrium, it is K into theta. So K is provided in the problem, that is 0.15 into 10 raised to power minus 6 into theta is also mentioned here, 40 degree. So what should be right here? 40 into pi by 180, because we have to consider radian. If there is angle straight away without any sine or cosine, then we will have to consider in radian. That we need to take fine care of that. So what will be the answer?
1.04 into 10 to the power of -7.
1.04 into 10 raised to the power -7 Newton meter, isn't it? Anyone else getting the same value? Okay, so the answer is 6 micronewton meter. So please recheck with your calculation. It should be 6 Newton meter, 6 micronewton. Okay. Okay, so let us move ahead. Wait. Uh, K is itself given in degree, right. So theta should be in degree. So we can take a straight away 40 degree here. No need to convert into radian. Right, so we can remove it. Yeah, your calculation is correct, but this approach was wrong. My approach was wrong. So here, since you have to take care of this K, so K is already mentioned in per degree. So micronewton meter per degree, and then you'll have to multiply with degree, then you will get the value in micronewton meter. So your calculation was correct. It's mistake from my side. I should have considered it. So it should be 6 micronewton. Is it fine?
Right, sir.
Now, the second part, since we have calculated TD, the second part we need to calculate the meter current. Calculate meter current when the deflection is 40 degree again. Okay, so now we need to calculate the meter current. So how to calculate? We have the same expression, isn't it? Torque we know, If dm by dt. Okay, is equal to 6 micronewton meter. When theta is equal to 40 degree, torque is 6 micronewton meter. And when there is no information given, you can straight away consider Im is equal to If is equal to I. That both the coils having the same current. Now I square dm by d theta is equal to 6 micronewton meter. Dm by d theta can be calculated at 40 degree. Since expression of m was provided here, isn't it? 500 sine theta minus pi by 9. 500 sine theta minus pi by 9. So we can differentiate it further. Dn by d theta to 500 cos theta minus pi by 9. Okay, so this is the differentiation. Now we will need to plug in the value of theta equal to 40, or 40 is also mentioned in radians. So 40 is equal to 4 pi by 18. So theta we will have to plug in 4 pi by 18. So then the value we will get 500 cos 4 pi by 18 minus pi by 9. So 2 pi by 9 minus pi by 9 is equal to pi by 9. So 500 cos pi by 9. So you need to calculate this value to get dm by d theta. And torque we know. So 6 micronewton meter is equal to I square into 500 cos pi by 9. So from here you will get I is equal to 6 into 10 raised to power minus 6 divided by 500 cos pi by 9. Isn't it? So how much this value will be? Okay, so for you, let me tell you the answer. You can match it with your value. So 0.113 ampere. So this much of meter current will flow, right, when the deflection is at 40 degrees. So when this much current will flow in the circuit or in the coil, your deflection will show 40 degrees. Okay. Is there any doubt in this? So I hope based on these type of problems, you are able to solve your week one assignment, which is due by tomorrow, I guess. Okay, so shall I move on to the next topic, which is okay, great. So, which is electrostatic instrument. So now we just saw electrodynamic instrument. We will see electrostatic instrument. What is that? Why do we use electrostatic instrument? So in electrostatic instruments are used to measure the voltage rather current. And here capacitors are used. So a parallel plate capacitors are placed. One is fixed, one is variable. You might have gone through the lecture. So in electrostatic, the more voltage will be there. Okay, the plate will move apart. So here, force. What kind of force will be there? Electrostatic force will be there, which is related to capacitor. So torque should be electrostatic. So one thing is sure that torque is proportional to force. Okay, and force is proportional to charge in what way? Q square. Why Q square? Because from Coulomb's law also, if you see, there are two plates, isn't it? Plus Q minus Q. There will be force, and this force will have the magnitude. In magnitude, it will have Q square, right? And Q square charge will have the dependency on voltage. The more there will be charge, the more will be voltage. So it will be proportional to voltage. Okay. So finally, we can see that torque is varying with V square. I hope it is fine. If not, please stop me in between and ask the question. Okay.
Yes, sir.
So if we remove the proportionality, we will have K1 V square. And again, this is being managed with a spring. So we will have at equilibrium to equate with a spring constant that is K theta. And here theta will be K1 by K V square. So which we further can say K dash V square. So the deflection of pointer will be depending on the magnitude of voltage. Okay. So again, it is non-linear device because it is varying with the square of voltage, right? And i- if the voltage is AC, then we will have to take V RMS square. Okay. And from class 12 physics, we know the expression of capacitor, that is A epsilon by D. So epsilon is generally epsilon naught into epsilon R. Okay. So yeah, any doubt there? So this plate are placed like in this manner, which is fixed. Let's suppose it is fixed, and this is like this, and it is moving. It can move. This has minus q, this has plus q, and this plate can move. Okay. So now, what should be variable here in the expression of capacitor? Because once the voltage will be applied between them, there will be force. Okay. And since in normal circuit, both the plates are flexible or fixed, so that none of the plates move. But here, intentionally, one plate is kept fixed and one is kept flexible to rotate. So one plate has to rotate because of force. Because of force, there will be some torque. Okay. So the position which is changing, if this plate will either move in this direction or this direction, the position is changing itself. So capacitor will be variable, isn't it, with position, and that will change the area what is covering. So there are proper forces being applied here. Now if this, let us suppose some voltage is applied and this plate has been shifted to this position, so now the force is only this much, right? So not maximum forces is being exerted by each other, but still there are some quantity of force will be identified or can be represented with a theta. So how much area is being changed here? So area is changing, area keeps changing, and that with epsilon by d. So here, so in electrodynamometer, our inductance was variable. In electrostatic instrument, capacitance capacitance is variable. Okay, is there any doubt? And generally, these plates are semicircular or one quarter of a circle. So I did not draw it properly, but this is like one circle, and generally the plate area or plate is made in such a shape like this. So this will be your plate. Okay, and the rest will be, yeah. So this will be the shape of plate generally, so that we can calculate area quickly because we know the area of circle pi r square. So the area of this kind of capacitor plate will be pi r square divided by 4, isn't it? And how much area is being shared by each plate will be defined by that A theta we will have to define. So A theta A theta will be pi r square by 4 into theta by pi by 2. This pi by 2 can change. That depends on how you are calibrating your instrument, up to which angle you are selecting for full scale deflection. Suppose you are saying that I will have full scale deflection at 120 degrees. So there you will need to incorporate that value. You will have to change it with 120 degrees or 2 pi by 3. So that is why pi by 2 is coming here, and theta is how much the plates had been moved from the original position. Okay. So I hope it is clear. Now, so we calculated capacitor which is varying with theta. So now we are expected to calculate the expression of torque, isn't it? So torque expression will have V square for sure and into half into dc by d theta. Okay. So, energy. So it is being derived from, this expression. Energy is half cv square. So torque can be derived from this expression, and that is why this factor of half is coming here. And since capacitor is being varied with the position of the plates, for dc by d theta, you have over here.
Yes, yes, sir.
So, yeah. So what's left? Nothing. We are done with. We are cool with torque. So this torque is expression is this much, and at the equilibrium position, we can equate it with k theta. Okay. Great. I hope if there is any doubt, please ask. Otherwise, we will gain more insight of this electrostatic instrument with one problem. Okay. So let me see if there is any doubt. Yes, a 2 meter voltage. Yeah. Okay. So the question is, we have a very simple electrostatic instrument. Okay. Again, it is consisting of two semicircular conductor plates. So semicircular conductor plates. Now, one state and other will have to rotate parallel to the fixed plate, such that overlapping area between them can be varied. So radius of plate R is given 6.5 centimeter. Okay. Perpendicular distance between the plates is again 9 mm. Now a spring constant is also mentioned, 0.2 micronewton meter per degree. We will have to give a special attention to this unit per degree or per radian. Okay. So we need to find deflecting torque if the voltage is 1.3 kV applied between both the plates. So we'll have to calculate TD, deflection torque. So since it is semicircular plates, the area of semicircular plate is
Half pi.
half pi square. Great. Now we are done with area, but it will vary, right? Area will vary, so a theta also will have to. We should write it here right now into theta by pi or theta by how much? It is varying that information. Theta by hmm, theta by pi by 2. Okay. So now next thing, what should we do? Because deflection is not mentioned. So we cannot go ahead with deflection torque is equal to k theta like last question. So we will have to calculate TD is equal to half V square dc by d theta. Okay. And this first we need to define C. C is equal to half how what a theta into epsilon by d, and a theta we have found that pi r square by 2 into theta by pi by 2 into theta by pi by 2. Okay. Epsilon, we know 8.85 into 10 raised to power minus 12. Is it correct?
Yes, sir.
And
That's
thanks. So, and D is, yeah, and D is 9 mm. So 9 into 10 raised to power minus 3. So we just need to calculate it here. So C will be by 3.14. R is radius of the plates are given 6.5 centimeter. Into 2 by pi. If you take this 2 on numerator side into 8.85 divided by 9 into 10 raised to power minus 9 into theta. So dc by d theta will have the same value, isn't it? So it will have this value basically. So you need to calculate this to get the answer of dc by d theta. And after calculating dc by d theta, can anyone let me know what will be this value?
8.30 into 10 to the power minus 12.
8.30 into 10 raised to power minus 4. This is the value of dc by d theta, right? So farad per degree. Now, to calculate the torque, we will use V square by 2 dc by d theta. So V is given 1.3 kV, 1.3 into 10 raised to power 3 square divided by 2 into the value is given 8.3 into 10 raised to power minus. So this will have
Sir,
Newton meter. Yeah, please go ahead.
4.15 into 10 to the power minus 12 होगा सर.
Into minus.
ये नहीं सर, ये ऊपर वाला वैल्यू.
अच्छा, dc by d theta you are saying?
हाँ हाँ हाँ.
How much?
4.15 into 10 to the power minus 12.
into 10 raised to power minus. Okay, okay. So we will discard this value and we will use this value here. 4.15 into 10 raised to power minus 4. So please let me know this answer with multiplying with v square by 2.
1.75 into 10 to the power minus 6.
1.75 into 10 raised to power minus 6 Newton meter. Okay. Okay. Great. Thanks. So this is the value of torque, right? But one more important thing, which I think I did not explain properly, is how to take this in area. A theta is equal to area, whether it is semicircular plate or 1/4 of the circular plate or whatever, which is pi r square by whatever, into theta by this denominator. Okay, how to select this denominator? Because here we have committed apparently a mistake because we did not. What happened? Yeah. So here, mm,
Pi by 2.
yeah. So I hope it is visible, right?
Yes, sir.
Okay. So here we have considered pi by 2. Okay. But pi by 2 we took in theory when it was 1/4 of the plate. So let us draw it. And with physics, we can understand it very easily. Okay. So this is the position of plates when they are facing each other. So at this position, the force will be maximum. Okay. Now, why we are considering, because if you see, this is the position we will consider as theta is equal to 0 degree. Okay. And let us suppose these plates are moving in this direction. Okay. Now, from theta is equal to 0 to this position is theta is equal to 45 degree. I hope you agree this position. Okay. If plates are coming at till this position, let me draw also this one. And here theta is equal to 90 degree. This position is theta is equal to 90 degree. Now, till this position, the plates are having some, crossover, some linkage. When these plates are moving till this direction, till this position, the new position, when plate will come to this new position, then there is no interaction between both the plates, right? So as soon as this plate moves apart from the theta is equal to 90 degrees, there will not be any forces between both the plates. That is why in semicircular plates, we were considering theta is equal to, sorry, in one fourth of the circular plates, we were considering A into theta divided by pi by 2. I hope you are getting where I am going to land. Now with circular plates, what will happen? Sorry, semicircular plates. So again, we will consider this as origin. Theta is equal to 0 degree. Okay. Let us suppose again it is fixed. It was also fixed. Now let's uh, this plate 2 has started rotating. Okay. So till the next position, theta is equal to 90 degree. What will be the position? The origin will shift here, the new origin, and the semicircular plate will have something like this. Okay. So at theta is equal to 90 degrees, still they have cutover, crossover. Okay. You see that theta is equal to 90 degree. Now, with next position, mm, yeah, with next position, this one, theta is equal to 180 degree. We will have, we will start having any, not having any interaction between both the plates. So in semicircular plates, we will have to change this theta with 180 degree. I hope you are able to get it. I can explain it once more if you say, okay. So we will have to observe where the interactions are getting over. Okay, till that angle, we will have to consider because that much area will be having the common forces between both the plates. So that is why here we should have taken here instead of pi by 2, we should have taken 5 because in semicircular plate, area will vary till 5. So your answer will change, but this is the concept behind it. I hope you got it, right?
सर्कल में तो कोई चेंज नहीं होगा सर, मान लीजिए प्योर सर्कल ही रहेगा तो।
हाँ, circle में till 2 pi, till 2 pi. In circle, you will have to take till 2 pi.
तो इसमें जैसे इसका डिस्टेंस पे डिपेंड नहीं कर रहा है सर, डिस्टेंस इसका थोड़ा सा बढ़ गया इसमें लास्ट
अच्छा,
पोजीशन।
your हाँ, I got your question. That is really a nice question. So you are saying that here, okay, let me say, here in semicircular plates or quarter circular plates, they have dc by d theta. So with theta they are changing, right? But in circular plates, everything is uniform, so there will not be any change, right? So that's what you are asking. Am I correct with your question,
यस सर।
Niranjan? Okay, yeah.
यस
So
सर।
in circular, yeah. So in circular plates, see, uh, how can you make circular plates? If you make circular plates, then of course there will not be any change. And in that case, the plates should not have any displacement along the axis. They should have displacement, in translational side. Otherwise, there is no point of having circular plates. So that is why generally circular plates are not used in such type of instruments. But if you are going to use, then you will have to move them from each other so that the area should vary between them to produce the torque. So in common capacitors, we can use circular plates. There is no issue. You might have seen circular plates in 12th class physics also, but here there are no use of circular plates because in uh, common capacitors we do not want to apply any torque or we do not want our capacitors to move, right? So that is why circular plates are very common there. But here we do not want our we want our capacitors to exert some force so that some torque should be required and they should rotate along the axis.
Yes, sir.
Is there any other question? Okay, so this was the deflection torque. Now the second part is very easy. We need to calculate deflection theta if 1.3 kV is applied. So since you have calculated torque, we have to just equate with k theta, and k was mentioned in the problem. Isn't it? So k is mentioned here, 0.2, and theta we need to calculate, and torque we have calculated. So 1.75 into 10 to the power minus 6. I know this might change with when you replace theta with pi in semicircular plates, but for time being we can go ahead with this, and you can calculate your theta equal to torque by 0.2 micronewton meter per day. Okay, so you will get theta in degree. If you are being asked in radian, be aware of that. Okay, so that's how you will get how much deflection is there with this much of voltage is applied. So here you can see the deflection is varying with voltage. So more the voltage, more the deflection will be. Okay. So this is all for your assignment one. This much theory is more than enough to solve, and all the problems which are asked for week one assignment you can solve based on all the problems we have solved in our session. So I hope you are not finding any difficulty in week one assignment. If you have any question, you can ask. Of course, answers are not allowed to be mentioned, but concepts we can discuss. And if there are no any doubts, then we will move ahead to next topic, okay, which is ammeter, voltmeter, AMI instruments. Okay, so let us move ahead with the new topic. Yeah, so this chapter, which is named as a ammeter, voltmeter, ohmmeter, we will discuss about all of them in detail. So basically, how to connect ammeter, voltmeter, and how to connect external resistance, that is very important here. So we will start with very basic, and I hope you are aware that all these instruments, PMMC, electrodynamic instruments, can be used as ammeter. Okay, so ammeter have a parallel resistance which is tuned to, to change the range of the ammeter. Along with that, ammeters are generally connected in series with the branch where you want to measure the current. Okay, so that is very basic theory. Now, full scale deflection and change of range in ammeter. So let me write it here. So let's suppose one ammeter has full scale deflection of 10 milliamp. Okay, so if it is so, this is 10 milliampere, so 10 milliampere will come out. If I want to increase the range of this ammeter to 100 milliampere, what we will have to do? We'll have to connect one parallel resistance, shunt
Parallel.
resistance. Exactly. Okay. So I think very basic thing of very basic part of this concept we have already discussed a bit, but still we will go from basic and we will base our all the concept on this. So how to connect both combination of voltmeter and ammeter in a circuit, how much errors are there. So all these things we are going to discuss. How much errors should be and which parameter affects the most to produce the error in the circuit. So that we are going to have. So now we want to have a range of 100 milliampere. So we cannot change this ammeter. We cannot change this much. Okay, this much is fixed. But what we can change, when 10 milliampere is flowing here, 100 milliampere should flow here. So for that, we are doing all the manipulation. So for that, here, the current should flow 90 milliampere, isn't it? And with ammeter, you will always be given with internal resistance of the coil. So internal resistance of the coil, internal resistance of the ammeter, which is what? Which is 99 ohm. Suppose it is the resistance of the coil. Now we have connected one shunt resistance. So since we have the value of full scale deflection and resistance of the coil, so we can calculate this voltage, isn't it? So this voltage will be 10 milliampere into 99 ohm. So we will have how much? 0.9 volt. This much voltage we have calculated. Now 90 milliampere is required in this shunt branch. So RSH we can also calculate 0.9 divided by 90 into 10 to the power minus 2. So how much will be our shunt? Our shunt will be 10 ohm, I guess, isn't it? So this much value of shunt resistance we need to connect to increase the range of this ammeter from 10 milliampere to 100 milliampere. I hope it is fine with you. We have already discussed this. Now we will come to multi-range ammeters, based on which many questions have been asked in week 2 assignment. Okay, so what are multi-range ammeters? So it is nothing but similarly, we are denoting an emitter with resistance and current source. Okay, so again, 10 milliampere and 99 ohm. Okay, so this is your ammeter. Now we can have multiple range of this emitter, like from 10 milliampere whenever we want to 100 milliampere, whenever we want to 1 ampere, whenever we want to 10 ampere. So one very obvious question will come in your mind, that why will we keep changing from 100 to 1 to 10 if we know the maximum value of the emitter or maximum requirement we want up to, let's say, 100 ampere. We want to increase the range from 10 milliampere to 100 ampere. So why to have multiple multi-range emitters? Why to have multiple switches? Because multi-range emitters is being accomplished with multiple switches, which will be like this. Let me show. Okay, with different value of resistances. Okay, so this is your connector, and it can have the switch. It can be put to here, it can be put to here. So you will ask that if we can design it for maximum capacity, then there is no need to go at the intermediate state. We can skip that. That is very obvious logic. And the reason or the answer for that is, if you are going to measure 10 milliampere and you have an emitter with range of 100 ampere, it is gonna give you a lot of error. So you will not be having precise and accurate value, and very far from accuracy. So that is why we generally connect emitters, or we want to have emitters which have the range very close to the measured value which we are going to measure. Okay, so that is the concept behind it, and how all of them will vary, that we will also see with problem. Okay, so let's suppose this resistance is 11 ohm. This is 1 ohm, and with 11 ohm, this range is being extended to 100 milliampere. If you calculate, you will get the exact same value. With 1 ohm, your range will be increased to 1 ohm. Okay, with 1 ampere, your range 1 ampere will flow here, 100 milliampere will flow here, and again for 10 ampere, you can calculate this resistance. Okay, so that was mentioned in the lecture. Okay, so this is the multi-range emitters. Now let's quickly discuss about voltmeter. Then we will talk with combination of voltmeter emitter, which is very important. Okay. So similarly, since emitters will have shunt resistance, voltmeters will have series resistance. Okay. So with series resistance, you can increase the range of voltmeter, right? So on an emitter can also be changed to voltmeter by connecting the resistance in series. So let's suppose one PMMC emitter has range same, that is 10 milliampere. PMMC has FFD is equal to 10 milliampere, and the resistance is equal to 100 ohm. Now we want to make a voltmeter with range of 1 volt. Okay, 1 volt range. What will we do? We will first draw this 10 milliampere this 100 ohm. And if you calculate voltage among them, that will be your voltmeter reading, isn't it? So how much will be the voltage? That will be 1 volt itself. So no external resistance is required. Okay. Now further, if you want to increase the range to 10 volt, from 1 volt to 10 volt, okay. So now what should we do? We will have to connect one resistance in series, which should have the drop of 10 minus 1. So it should have the drop of 9 volt. Okay. So 9 volt, I hope you are able to understand this. So 9 volt will have series resistance of 9 and current is same, that is 10 milliampere. So you will have how much? 900 ohm. So this much series resistance. So this is how you easily convert an ammeter to a voltmeter, right? Or you can change the range of voltmeter also with the help of series resistance in an ammeter. So I hope there are no any doubts. If you have, please ask. And since ammeters are connected directly with series to the branch where we want to connect current, voltmeters are connected in parallel. So you will apply one terminal of voltmeter here, and you will get the voltage. Okay. Now, the thing is, why there are errors in the circuit? So let us go ahead and see. So let us suppose this is a battery with voltage of 10 volt. Okay. We want to connect with, but it is unknown to us unless we are going to apply voltmeter or we are aware of the rating of this battery. We don't know the voltage of the battery, right? So let us suppose it is unknown to the person who is going to measure this. So he is going and connecting the terminals of voltmeter like this at this both terminal. Okay, what will happen? Will he get exact value of 10 volt or will he get something different?
Less than 10 volts. Because of
Less than 10 volt. Exactly. That's right. Great. Because voltmeters will have one internal resistance also. So some voltage will be dropped across that internal resistance. And that is where your errors will arise. Okay. So now all the control you have in your hand is to control this resistance. None other than this. Okay. So how to control
yes.
this resistance? So a smaller the resistance or larger the resistance that we are going to see. Okay. So now let us see, or let me change this circuit a bit and let us see what will happen. Let us suppose, because any battery voltage will have some internal resistance. So let me call it Ri. Okay. And one voltage of same voltmeter along with its resistance R. So this much is the voltmeter part, and this much is the circuit which will have some resistance. Okay. Now, voltage measured should be ideally or accurate voltage is how much? Some current will flow here. So 10 minus I into R. But voltmeter will measure will be 10 minus I into Ri plus Rn. Okay, so this will be the measured value and this much will be the required value, isn't it? Now, there is difference, okay, and that difference is the error. The error is, okay, let us find the error. Error is E minus I into Ri. This is the, exact value, E minus I into Ri minus E into what we will measure, right? So E minus I into Ri plus Rn divided by exact value, E minus I into R. Okay. So what we can say, that we can take E minus I Ri common, 1 minus 1 plus, this will have plus Ri plus Rn divided by E minus I into Ri. So it will cancel out, divided by E minus I R. Okay. So this will also cancel out, and we will left alone with error is equal to Ri plus Rm divided by E minus IRi. E minus IRi. Okay. And further, if you want to take in terms of I or Rm, it should get cancelled. Okay. So if you solve it, like I is equal to E divided by Ri plus Rm, E minus V, E minus B. Okay, I think I complicated this calculation, but finally what you will get in terms of error, I am straight away writing, that will be 1 minus Rn divided by Ri plus R. So this is what I mean to calculate it here. And further, if you solve, you will get Ri divided by Rn. Okay, and percentage of error will be Ri divided by Rn into 100. So this Rn, the the conclusion of all this analysis is, the higher the value of Rn measured resistance of, or the voltmeter resistance, series resistance, lower will be the error of the circuit. But this is not always true. Okay, in some cases it will change when we connect both the combination of voltmeter and ammeter together. But when we are going to connect voltmeter, that series resistance should have very high value, so that we will get very less error. Okay. So ideally, we say that it should have infinite resistance, but that can never be possible. So Rn should be as large as compared to Ri. Okay. And in complex circuit, if you go, you need to calculate, Thevenin resistance. That will be your Ri of the circuit. So let's suppose there is a complicated circuit. So what you should do, you should calculate Thevenin resistance of that. And this Thevenin resistance is nothing but your Ri, and it should be less than Rn, isn't it? Then your voltmeter will work properly. Okay. Is there any doubt in this voltmeter?
No.
Great. Now, finally, ohm meter. We will discuss ohm meter. Ohm meter is also same. It measures the resistance, right? But its calculation. If you see the problem based on ohm meters, it's bit complicated because it has certain characteristics which we want and which we will use in this concept. So let's suppose one, again one voltage source. Let me, yeah, yeah. So one voltage source is there, isn't it? And along with that resistance, along with that current, with ammeter. So we want to measure this Rx. Okay. So meter is nothing but to measure the resistance, and resistance can be measured when we connect one voltmeter along with the resistance and one ammeter along with the resistance. So the straightforward thing to calculate resistance is nothing but voltmeter reading divided by ammeter reading. Connect voltmeter in parallel and connect ammeter in series. You will get the resistance. But will it be accurate? That is the question. And that is what we are going to calibrate in our case. Okay. Mm. Okay, so voltmeter has something like this. This is the center part. This is extreme right. This is extreme left. And we want our voltmeter pointer to be placed in near to the center point. Why? There is a reason behind that. Because extreme right side, this is considered as 0. And extreme left side, it will have the maximum value. But we want to have accurate value or accurate measurement of the resistance. We want our pointer to lie near the center. Why is that? We are going to see that. Okay. So now let's suppose a circuit similar to the previous circuit. Any circuit has some internal resistance. Okay. So circuit will have internal resistance which will comprise of you know Ri plus ammeter plus some other. Like if you have gone through the circuit, let me draw the circuit for you. So if you have gone through the lecture, this kind of Ri, okay, this this is the Rx we want to measure here. So here we will connect one voltmeter and ammeter. So R1, and this is the ammeter resistance R. Okay, and this is your Rx. So here we want to measure resistance. Okay, here we will connect and we are going to get the value of Rx. Right? I hope it is clear till now. Now, if Rx is 0, if suppose this resistance is 0, because Rx what we are going to measure, right? Then the value of this all current, whatever is flowing here, I will have the value of full scale deflection. I is equal to I full scale deflection. Okay. So that is why in our internal, we will collab all the resistance R internal is equal to Ri plus R1 plus Rn. This is all R internal. And when Rx is equal to 0, of course, then current will be maximum because external resistance is 0. When you are measuring the resistance 0, it means the current should be maximum. And that maximum current should be full scale deflection. And that is why this full scale deflection will have the magnitude of E by R internal. Is it fine till now?
Yes.
Okay. Now, further, if there is some resistance, okay, which we are going to measure, that should have, it means Rx should be finite. Okay. When Rx is finite, then I is equal to E divided by R internal, because R internal is something which should not change, because that will always be there. That can vary beforehand, but once it is fixed, it is, there is nothing in your hand, and you will get some error that we are going to see. So it will have the magnitude of current, which is equal to E divided by R internal plus Rx. Okay, it will certainly be less than I full scale deflection. Okay, now one criteria what I am saying, when R internal is equal to Rx, then the current will have IFSD by 2. Do you agree with me here? See this expression, when Rx is equal to R internal, then what happens? I is equal to E divided by 2R internal, and E divided by R internal is I full scale deflection. So current will have half of the full scale deflection. So your pointer will move. This is the IFST. This is the IFST point. It will move from here to the center. Are you getting it? So pointer deflection is right now 50%. 50%, yeah. So deflection is 50%. Any question there? Now, why are we insisting on 50% deflection or half a scale deflection? That we are going to see with one example. Okay. So, this example we are saying, which is also mentioned in the lecture notes if you go through it. Okay. So, R internal is given as 1 kilo ohm. Okay. And Rx is equal to 0 is full scale deflection that we know. Okay. Now, this 1 kilo ampere, sorry, 1 kilo ohm is your resistance. If you have the resistance external, Rx is equal to, if your Rx is equal to double or half, okay. So Rx is equal to 2 times R internal. This is case 1. Where will pointer be lying? And when case 2, when Rx is equal to half of R internal, where the pointer will lie. Okay. So of course, when Rx is higher, then your pointer will shift towards the left of the center point. So this is your, let's suppose, center point. Okay. Now here in this case, I will be how much? E divided by R internal plus Rx is nothing but 2R internal. So it is nothing but E divided by 3R internal, nothing but IFSD by 3. Okay. Similarly, in this case, so IFSD by 3, it should lie towards there, somewhere here. Okay. IFSD by 3 corresponding to Rx equal to 2R internal. Okay. For second case, I is equal to E divided by R internal plus half of R internal. So 3 by 2, 2 by 3, IFSD. So 2 by 3 IFSD will be closer to this side. Okay. So 2 by 3 IFSD and corresponding half R internal. So the higher the resistance, it will shift left of the center point, and for infinity resistance r tends to infinity, the pointer will be like left at leftmost. Let's suppose it is the limit of the ohm meter, so it will lie here, not here. Mhm. Yeah. And it will lie here when Rx equal to 0. Okay, this is the thing. Now, our analysis was to find out why center point is very crucial to have very low error. Okay, so now we will have for same circuit, we will have Rx equal to 30 kilo ampere, and this R internal is as it is 1 kilo ohm. Okay, now we will see how much error will be there. Rx equal to 30 kilo ohm. If we want to measure, okay, then what happens? If I current will be, because this 30 kilo ampere, what is happening with it today? So this 30 will have, it is 30 times of R internal. Okay, if you remember, R internal was 1 kilo ampere. So current will have E divided by 31 R internal. Okay, and E divided by 31 into 1 kilo ohm, so 31 kilo ohm. Okay, so current will have some, let's suppose E is also equal to 100 volt or something. So 100 volt by 31 kilo ohm. So some value it will come. Now, if your circuit has 35 kilo ohm, let's suppose Rx is equal to 35 kilo ohm. So now your I will have E divided by 36 R internal, which is not much different from this value. So difference you will not be able to analyze. Okay, and hence you cannot appreciate the difference between your resistance. What is the external resistance you are going to connect in the circuit? So the conclusion is, if external resistance is very significantly higher than your internal resistance, then you are not going to read very easily, or there will be high error in the circuit. So you will not get the exact value of your external resistance. On the other hand, if you have external resistance very close to your internal resistance, it means your circuit will show you close to accurate reading. Okay, and of course, this condition Rx is equal to R internal will show your pointer in the middle at center. Okay, so that is why we kept emphasizing that center point is why important very much, because if your pointer is lying in the center of your ohm meter, it means you can interpret that your circuit is showing close to accurate value of your resistor. And if it is much towards the higher side or left of the center or right of the center, then you can see that there are some errors you are going to get. Okay, so I hope I am able to comprehend this concept. Is it fine for you? Any doubts there?
Yes.
Great. So for that, what generally we do, because every time we cannot keep changing, because let's say we have purchased one ohm meter of internal resistance of 1 kilo, okay, and we have requirement to measure the resistance of 30 kilo. So we will not go again and buy different ohm meter again, right? Because that will be violation of the purpose. So what can be done? You can change the internal resistance then. You can tune the internal resistance. How? By connecting one more external resistance to the circuit. Because let's suppose if you have to measure 30 kilo ohm and what is external resistance, and you have internal resistance of 1 kilo. Now what should we do? We can connect one extra resistance, one additional resistance, which I'll call it, that should be close to this total R external. So additional should be 29 kilo ohm. Now you are going to get your pointer at the center with this value, and your ohm meter will show very precise and accurate reading. Do you agree now? So
Yes.
that manipulation you need to do in the circuit, and that is how questions will be asked based on this concept of ohm meter. So center position is very crucial. So let me conclude in some points of ohm meter. Try to maintain pointer at center or near center, and try to maintain Rx is close to Rx. These 2 points, if you keep in your mind, you can solve any type of problems. We will solve in next lecture some problems, okay? But these two takeaway you will have to get to understand this ohm meter or solve this ohm meter very effectively. Okay, so that's all. We have seen the theory behind ohm meter, multimeter, multi-range ammeter, multi-range voltmeter. So from next lecture onwards, we will solve some problems based on that. And I hope you are able to solve week 1 assignment. Please solve it carefully and get the concepts very crisply and precisely, so that in exam you will not be needed to waste much time in solving all the questions. So is there any final doubt before I conclude the session? Okay, so let us meet next Tuesday. So thank you very much for joining, and keep attending these lectures. Thank you very much. Have a good night. Bye. Thank you. Thank you, NS.